Okay, if everyone wants to take their seats, we're going to get started here. Perfect. Okay, I hope everyone's well caffeinated. I know my hands are shaking, so I'm definitely on that level. I'm very excited to introduce our keynote speaker for our conference this year, Dr. Patrick M. Pilarski. He's a Canadian CFAR Artificial Intelligence Chair, past Canada Research Chair in Machine Intelligence for Rehabilitation, and an Associate Professor in the Division of Physical Medicine and Rehabilitation at the U of A. He's a fellow and vice board chair at AMI. He co-leads the Blink Laboratory and is a principal investigator with the Reinforcement Learning and Artificial Intelligence Laboratory at the U of A. As part of this research, Dr. Pilarski has developed and made prominent machine learning techniques for continual sensory motor control and prediction learning on prosthetic devices. These include approaches to ongoing user training of upper limb prosthesis control systems via reinforcement learning. He is also pioneering the use of general value functions in prediction learning to continually adapt myoelectric control interfaces in real time. That was a lot of words. Without further ado, I'm going to introduce Dr. Pilarski.
Thanks so much. Oh no, and now we just seem to have popped out of our, let's see, how do we get back to slideshow mode? Awesome. That's always awkward when people are like reading about you and then you stand there and then you have to listen to them talk about you and then use all sorts of complicated words. Anyway, thank you so much for having me. I'm really excited to be here. The topic of today is something that I'm really excited about, and it actually represents a step change in thinking that I think we've come to in our group, especially over the last 2 to 3 years. I will also note up front that a lot of this work is done in collaboration with my good friend and close collaborator, Dr. Jacqueline Hebert. So I want to also give a shout out to Jackie because she's amazing. And you'll see some work that is directly related to things that she has brought to Alberta. So let's make sure this actually works. Does it? Okay, cool. So the way that I really want us to think about this is not that the other fancy title, but this really is to make a case that humans and the assistive technologies they interact with should both be continually learning and changing and improving as they interact. So if you just like now you've burned through all of your coffee already and you want to go to take a nap, that's fine. We're already at the main message. So COI disclosure, just want to say, while I was a employee of DeepMind while some of this work was going on, and also that I'm on the board of directors of AMI, the Machine Intelligence Institute. Okay, so here's the statement that I think I'm there's this podium's in the way. I'm gonna go over here. This is a statement I think probably many of us will agree upon. Maybe some of you don't, but I think it's probably a very agreeable statement, which is that the control and feedback, the way that we choose interventions and how we train people to use assistive devices can be improved through adaptation and sculpting to individuals, their unique needs and their unique daily life. So probably everyone's like nodding, yep, that is a thing that we all agree on. And the statement, though, that then might be controversial or we might not all agree on is that those same assistive devices should continue to change and adapt and be sculpted to individuals after they are deployed, after their like post-clinical deployment. So to sort of introduce this, I'm going to show with like little meeples and block diagrams here. So humor me and say that this little gray person here that you're seeing. Am I getting out of the camera feed, by the way? Maybe I should go back up over here. Okay, I will. I'm sorry. Okay, I'm bad at staying on camera. So imagine you have a person and a device that I'm showing in this diagram right here. And this little arrow is showing that, in fact, the device right now is adapting to the person. This is often what we see when we have in the clinic, a device will be adapted to the person who's going to be using it. And then over time, for the rest of time, all of infinity, the person will be adapting to that device. So that's what these little arrow notations mean. Recently, we have seen a change because of things like machine learning as deployed in clinical settings, especially in upper limb prosthetics. That's the area that I work in. We start to see now that, well, okay, at certain times, a device will be adapted to the person. The device will change or improve in response to the person. And then the person will adapt and change for other sustained intervals to that device. And then that repeats until the end of time. Very recently, especially in upper limb prosthetics, people have figured out big data's oh my goodness, big data, and decided that, oh my goodness, we might be able to use like information from other people to also adapt that same device at intervals. So this is something that's just starting really to hit the mind space of people in the field of upper limb prosthetics, but in other assistive technologies, this has already happened, and some it's yet to come. The view, though, that I want to share today, and that we're going to talk about for the rest of the, say, 45 minutes, 40 minutes we have remaining, is the idea that, in fact, we don't have to think about it in terms of these intervals, in terms of these sort of stages of adaptation where one party adapts the other, that the adaptation can be continual and continuous on the part of both parties, and that modern technology makes this possible for the first time in our history. Okay, cool. So by the end of this, I like to put up objectives. I'm hoping that all of us here in this room could go out to lunch break and have a shared set of terms, things like constructivism and continual learning. And we'll also have, to have our discussions, a minimal set of concrete examples we can use to start to talk about what's technologically possible right now. And then we can start to discuss the similarities and differences of the different pathways I just showed you. So that's my sort of roadmap for today and the objectives I have for our time together. So those who've seen my recent talks know I like to jump to this slide. And I like to jump to this slide because this is the Cairo toe. It's an example of a prosthesis that was used by someone over 3,000 years ago. And the reason I like to show this is in part because there's evidence this device was adapted to its wearer over time. It was changed. But I like to use this as well to note that what we're talking about today with advanced biomedical technologies and the technologies for assisting humans is not new. We have used tools since before we were a species. Animals use tools as well. Over the epochs and over the thousands and thousands of years, people have adapted here on this exact place, in this exact land. People for like hundreds of thousands of years, time immemorial, have crafted tools, adapted themselves those tools, and those tools have been adapted to them. It's a socio-technical gyre that goes back literally hundreds of thousands of years. And so we start to see that gyre tightening. It's getting, the iteration cycle is getting faster and faster. I'll just switch to a snapshot of some of the technology we have just in our lab. This is just a video shot of some of the devices we have in terms of upper limb prostheses in our lab. And I think the reason I put that back to back with the Cairo toe is to say that there has been a revolution in sensor technology, the ability for systems to actually perceive the world, actuators and the actuation technology of systems. Computation has vastly increased in its capacity and power. There's now chipsets, there's actual computational devices that are customized for things like machine learning. And so we're now at a point where we can do something we never could before. In that entire history of people adapting to tools and tools adapting to people, we're now at a tipping point in history where our tools can now actively and proactively adapt to us while we're using them. And this is in a large part because of things like advances in artificial intelligence. So I'm going to take that view and zoom out a little bit for you into the underpinnings of how this all works. And so many of you are familiar with action, perception, and cognition, the idea that thinking systems like us will perceive the world around us. We will be able to act upon that world, and we'll be able to put that together through acts of cognition. Now, if we go back to thinkers like D.C. Engelbart, we'd see that the minute that we put a tool here I'm just putting like a stick in the hand of this individual that I rendered in Unity on the screen here. Put a stick in the hand of this individual, and you suddenly have an active extension. The ability to perceive the world is enhanced. The ability to act on that world is enhanced. And there's really some, like Engelbart calls this, the humans learning to use artifacts, methods, and tools, or artifacts, methods, and language in which they've been trained. Essentially a class of tools to enhance and extend themselves into the world. And there's some really great neuroscience literature that says that, in fact, our brains like shrink wrap around the tools we use. That, in fact, we do extend ourselves to encompass and embody those tools we use. So this is an active extension. It goes farther. So I have like the smartphone. We all know we can amplify our abilities by looking at our smartphones as we walk across the street and get hit by cars. But assuming that we're not doing something foolish like that, we do use our, whoop, that's the splash of the speaker there. We actually can amplify our abilities by way of our technologies. And Ashby, this is from 1956 and some of his work on an introduction to cybernetics. It's a beautiful book, but says that, intellectual power, much like physical power, can be amplified. Increasing our ability to select and choose and act is in fact a way to amplify our own cognitive abilities. I'm paraphrasing Ashby. And as that connection grows, we get to thinkers like J.C.R. Licklider from 1960, who talked about tight coupling between humans and machines. And here I'm showing you, like, looks like a fantastical diagram, but really it is a superposition of many biomedical technologies that are already available to us right now and common consumer devices. Put together, it is in fact a tight coupling, as that Licklider might have suggested. And I'll paraphrase Licklider from that same paper he wrote in 1960, which is that someday soon we might imagine that we will have tightly coupled systems of human machines that think like no human has ever thought and process information like no information processing system in the history of our species. So this is a very ambitious view, and I'm going to walk back to this by the end of the talk, but I think that we're actually at a tipping point now with technology where we can start to imagine what J.C.R. Licklider suggested as actually being what we now see. As a sort of primer on this, I'm going to break down all of those sort of glowing wires I showed you on the last slide into a different series of pathways. The first is a control pathway. And I think for those of you out there, I don't know how many show of hands, who actually works with assistive technologies and anything, exoskeletons, wheelchairs, prostheses. Okay, 1, 2, 3. Okay, like not that many. Okay, cool. How many of you use smartphones? Okay, good. So I'm at least safe. So now we have like the control pathway here, which you can imagine either being the mapping of, say, like neuromuscular signals from a person who's using an assistive device like an artificial limb. I'll ground everything in artificial limbs today because that's where I work and I'm most comfortable there. But it's also how you might imagine mapping your will and intent by way of your biomechanical motions to interact with any electronic or technical devices you use in daily life. The control pathway is just that, though. It's mapping the will, intent, or the intentions and signals from the human body and the human mind to the device that will then enact some form of them. And increasingly, machine intelligence is becoming the broker for that control pathway, mapping, in some cases, a small or limited number of signals that can be sampled from the human body, especially in something like upper limb neuroprostheses for people with limb difference, a small number of samples of signals from the human body to a large number of possible modes, motions, or functions of a device like an artificial arm and hand. Similarly, we have the feedback pathway. And so the feedback pathway is the way, it's actually mostly, I'm going to say mostly ignored, especially in upper limb prostheses to a large part, but is the pathway by which information that might be perceived or generated on the assistive device is actually transmitted back to the user, the person using it, the person who needs that technology. And for something like a robotic prosthesis used by someone with limb difference, it is largely like feeling the mechanical changes in the system, hearing the motors whir, someone actually looking as they're like grabbing an object and watching through visual feedback. We are starting to see, and our lab is doing some of this work actually, looking at machine learning now being the broker of that feedback channel, being able to help select and sample the information that is visible to an assistive device and help to transmit that in a timely, efficient, and effective way back to its user. So that's the feedback channel. And I'll also note that there's now an increasing number of surgical interventions for control and feedback that are really game-changing. Some of them include targeted muscle and nerve reinnervation. Essentially, our plastic surgeons going in and rewiring the nerves of the body so that we can actually take the nerves that would have gone to, say, an amputated limb and connect them to actual muscle tissue or to actual skin tissue to create a new bidirectional interface for people, say, with limb difference, or, in fact, osseointegration. I'll talk about these a little bit later on as well, but the idea that you might integrate like robotic systems like artificial limbs directly into the bone structure of the human body. So there's some really transformative surgeries, and actually we're doing all of these now here in Edmonton. It's pretty miraculous. And again, I'll show you some slides. The osseointegration, though, I will dwell on for 1 second more here because I just think it's so super cool. I mean, for like literally, look at that Cairo toe I showed you earlier. That was laced and strapped onto the body of the wearer. And now we have a surgery where you can, in fact, much like you'd install a hip implant for someone with hip replacements, you might be able to install a shunt directly into the bone of a residual limb of someone who's had an amputation and allow a robotic limb to be clip locked, essentially, just Allen keyed onto the bones of their body. And this is a paper from Max Tiz-Catalan and his team. And I think it's a great paper if you want to read it for those who like reading scientific papers, because what Max and his team has done has actually run wires through that same shunt so that you can, when you attach that robotic device to the bones of the body, you're also making an electrical connection directly to the muscles and the nerves. And you can see that in that X-ray, you can see that in the X-ray diagram there, I hope, if it's not blocked by the podium. We are doing some of these surgeries again here in Edmonton. This is a video of, let's see if it's playing. If it plays from the correct point, then everything is good. It is okay. It's from the correct point. This is actually Stephanie, who underwent post-surgery osseointegration at the Glenrose here in town, and she has osseointegration on her lower leg. And so what you're seeing here, this is like a sort of hot off the presses kind of video, is in fact the fitting of a microprocessor-controlled lower limb to Stephanie's leg. And so what you're going to see now is that the individual here is actually going to use effectively an Allen key to connect that microprocessor-controlled robotic leg to the implant that is connected to the bones of her lower body. And so now in a second, you're going to watch, and she'll stand up and take a few steps. She's actually has prostheses on both of her lower legs. One of them is osseointegrated, one is not. And we'll just dwell on this video one more time, because again, I think this is miraculous. Like we have a transition to a new phase of life as a species where we can actually connect our systems in a tight way we never could, tightly coupling in all sorts of senses. But anyway, I hope you find that very, very cool. Surgeries are happening now in Edmonton, and we're actually bringing them to the upper limb as well. We just got funding to bring upper limb osseointegration here to Edmonton. All right, that's really cool. That's why I want to dwell on it. So now, with all that in mind, like I showed you the control pathway, the feedback pathway, we talked about some of these revolutionary surgeries. I hope we can still all agree that prostheses can be improved through adaptation and sculpting to individuals, their unique bodies and needs. Like maybe just like a thumbs up or thumbs down from some of you. Like, okay, I've convinced a few of you. That's good. Okay, great. We're on track. I'm happy about that. Cool. And I will then say a little bit more boldly that modern prosthetic technology has the necessary preconditions to construct or enhance many of those elements during its deployed use and over extended periods of time. So now I'm going to give you some evidence for that, I promise. But what all hinges on is something that has come to be called continual learning, or the constant and incremental development of increasingly complex behaviors and knowledge. And this is from a technical field, there's some great survey articles I note down at the bottom here by some of my esteemed colleagues, but it really is the idea that as a field of machine learning and AI, or a subfield really, it studies how systems can continually learn, not just learn. Remember those little meeples and blocks I showed you at the very beginning, not learn in like training testing phases like many of you who do. Who does data science? Hey, data scientists? Okay, I see like 3 hands. Okay, awesome. So I'm very curious what all the rest of you do. We'll talk about that over lunch. But continual learning is the idea that systems don't have those sort of gaps between when a system learns and when it's deployed, that this is learning and deployment happen at the same time. And now you might ask, I'm going to focus completely on prostheses here, because I'm going to show you a trajectory of work from our lab that I hope is a sort of a representative trajectory. But what might a prosthesis control system, in this case, continually learn and use? One thing in the sort of pathway from data to goals by way of decisions might be representations, the structure of the world, the structure of information in that world. Another thing might be predictions, models, forecasts about how that world will unfold. And finally, another one, which is maybe the one we often focus on, is the actions the system might take, the way that it maps, say, user intent into the control of a neuroprosthetic device or assistive technology. For this talk, I'm going to focus almost exclusively on predictions, because the predictions have been, for me at least, over the last decade, the wedge I have used to inject continual learning and that idea of continual learning into the domain of upper limb prosthetic control, not just for us here in Edmonton, but for our global community. So I'm going to focus on predictions. Those of you who know about predictions, who makes predictions? All of you do. Your brain's doing it all the time. Thank you for raising your hand. But all of you are making predictions, and we'll talk about the cerebellum a little bit later. But really, predictions are central to almost all biological, maybe all biological decision making. Maybe I can't make that. That's pretty strong. But a lot of biological decision making hinges on predictions. And there's a couple of different types of predictions I want to call out too, in fact. One is a momentary kind of prediction. This is like, I hold you up a flashcard of something that's like done in like pointillism, and you're like, oh, I think that's a banana. Like, it's a prediction about what a thing is at that moment. This is often what we see a lot of, for those of you who do things like supervised learning or learning from labeled examples as a form of artificial intelligence. Those of you who work on that, often a lot of what we focus on is this sort of momentary style of classification. It's about the labeling or classification of a single instance or a set of data. There's also the idea of temporally extended predictions, forecasts about a window or span of time that it might be weighted according to some priority over that span of time. And so this is very much like we've put out a number of papers over the years on temporally extended predictions, but the whole idea of learning through trial and error, reinforcement learning, what's happening in the dopamine systems that you all possess inside your meat brains, all of that is in fact contingent on temporally extended predictions. And so there's these two types. I just want to call these out because mostly I'm going to focus on the temporally extended form. And again, all of these kind of predictions, whether they're momentary or temporally extended, they can be acquired or updated either in batches, like training and testing, like the intervals I showed on that first slide, or in real time. So these are two ways we might think about it. And those are all good. I'm not saying one's better or worse, but I want to point out that there are different ways that this can happen. And if for those of you who do like neuroscience and want to go read some great papers like Wolpert, Flanagan, and others, have some amazing papers on how prediction precedes control, especially motor control in the animal brain, and how, in fact, predictions are built up and used for the execution of actions, the kind of actions we do every day. And also that, in fact, some of the feeling of doing things, like the feeling of me like reaching down and actually doing this, might be based on the predictions of this as opposed to me actually doing it. That in fact, my feeling of agency and over my own actions is in fact the feedback mechanism from my predictions and not actually from my sensations. The sensations just correct the predictions. That's pretty wild. It's a great article in Science that I've cited at the bottom. If you want these slides, I'll put them on my website. So you can just go grab them and like download them in PDF form. So you don't have to take notes. I hope no one's taking notes. All right. So I will say as well that I am a reinforcement learning researcher, machines that learn through trial and error, or animals as well. And reinforcement learning techniques are very well suited to the continual learning of predictions. In fact, they are based on the continual learning of predictions about a special signal that we call reward. Okay, is everyone tracking so far? Is this cool? Great love for everyone. So far, everyone's having a good time, at least just surviving. Great. Okay, so I'm going to take a sip of water, and then I will dive into a key example from our work over the last decade that I think is a really neat sort of case example of how continually learned predictions can actually be used in assistive devices, and not just prostheses, but that's what I'm going to focus on. And this was the work on adaptive and autonomous switching, and this is mostly led out through the master's thesis of an amazing grad student I had, Ann Edwards, and her thesis captured a lot of the work that we've done on adaptive and autonomous switching. But I'll start this story a little bit earlier. I'm going to start this story with some of the early work we did with some of these individuals, participants who'd actually had that nerve reinnervation surgery. This is when we were first starting to connect those folks to robotic limbs and seeing if they could actually use their reinnervated muscles. Again, remember, reinnervation surgeries are all about rewiring the nervous system. So nerves that might have gone to an amputated limb now actually go to real muscles that still exist in the body. And we were looking at if these folks could actually use those reinnervated muscle sites to control robotic devices. And also, some of these were sensory feedback to see if they could actually feel what those robotic devices were transmitting back to them. And in that work, we also studied at the exact same time whether or not that same robotic device could be learning predictions, forecasts, temporally extended expectations about all manner of things that person was doing in their interactions with the device. I have a great slide with lots of boxes and arrows, but I skipped that today because it's just a slide with lots of boxes and arrows. But believe me, when I say that we looked at how a system, an assistive device itself, might start to predict everything from like how that robotic limb was moving, the signals flowing from the human body to it, the state signals that existed within the robotic system, and everything from the force to the velocities to the other dynamics of the person's interaction with their assistive device. Essentially building up a multifaceted predictive model of the person, the device, and their environment all at the same time, and all through just ongoing access to the data streams, continual learning. We showed not only could we do this for a few of the signals I just mentioned, but that it was highly scalable. Here I'm showing you one of the advanced prosthetic devices that we have at the University of Alberta. And we looked at not just making 1 or 2 or 5 or 10 predictions and learning them in real time, but in fact, tens of thousands of these predictions all at the same time. Now it's starting to sound a lot more like the cerebellum, but tens of thousands of forecasts about all aspects of the device being moved through the world, the signals flowing from a human body, loads, velocities, temperatures, and more. So we showed that not only can a system continually learn while it is deployed, like a prosthetic system, but in fact that this technology scales to the fact you can look at very dense data streams. And there's actually a cool, I don't think I mentioned it, but maybe it's next slide. Let's check. Sorry, you probably just want to watch the robot, but we do. No, I do. Okay, so we had a really cool paper called Predictions, Surprise, and Predictions of Surprise, where we showed that not only could a system predict the data stream, the bits of information flowing over the wires, that it could detect when it was wrong about those predictions, or that it could measure its own errors. In effect, be surprised. Wow, I'm wronger now than I was before, ever before in my life. And then start to actually predict those moments of surprise. Like there's one great video where I came up and like shook the hand of the robotic arm, and the arm, you could just watch its like digital brain flare up in the surprise centers because it's never been moved. It's never been back driven against its motors before. And then it could start to predict. When I did that over and over again, I put little weights on its hands and things. It actually could start to predict situations when it might be surprised in the future. So this is cool. And it was all learned through trial and error interaction with the world, through just raw data streams with the world, not through any kind of increments of training and testing. Okay, and I showed you that last drawing error in part as well, because what's really cool about this, as I mentioned the cerebellum earlier, is that the kinds of machine learning technologies I've been talking about, the kinds of root technologies, are in fact really darn close to the Purkinje cells that are like forming the basis of predictions in the cerebellum. So the way that you might start to make a massive number of forecasts about all sorts of aspects of motor control that in our cases does things like control our muscle tone and like our heart rhythms and things like that. In fact, there's a very close analog between the architecture I just showed you and the architecture of the cerebellum. You could almost think that this continual learning view that I'm pitching and the technology we deployed is like an exocerebellum, a small computational cerebellum that can actually be embedded within assistive devices. That's a very, very bold claim. You should come and like yell at me about it at the coffee break or whatever. But I do believe that there's some very nice links between this, and there's actually some good papers as well by my colleagues at the university. So mapping, the way that this works is, I think the reason I brought the cerebellum is because in the same way that when we look at cerebellar architectures, we can see that there's a mapping from predictions, learned predictions, to fixed control actions, a rabbit running through the brambles, and then like a puff of air hits its eye and its eye closes. It was predicting that its eye was going to get hit, but the response, the closing of the eyelid, is in fact a fixed unmodifiable behavior. So the mapping from learned predictions to fixed outcomes provides this amazing natural gateway to more complex and yet very highly adaptive interactions. Predictions that are learned through interaction can be used to change an interface. And that was the wedge. That was the wedge that we created that allowed continual learning ideas to begin to translate into the domain of upper limb prosthetics and assistive technologies writ large. And I'm still doing okay for time. Perfect. Okay, so adaptive and autonomous switching, I'll just pitch this a little bit more to you. Imagine you do have a neuroprosthetic device, like the big fancy robot I showed you on the other slide, or even commercially deployed devices that have many different modes, like many different grip functions, like key grips and power grips. A device that might have a flexible wrist or the ability to rotate a wrist. Often, because I'm just going to focus specifically on the case of limb difference due to amputation, the more that a limb might have been removed due to injury or illness, the less signals you have to record from in the human body, and the more functions you need to replace or to extend or to augment or modify. And so this is where adaptive autonomous switching comes in. In many clinical interfaces, not just in upper limb prostheses, a person might have just simple forward back joystick or a button push, and they might hope to map that single channel of control that they have to the opening and closing of a hand, the rotation of a wrist, the selection of different finger or grasp patterns. So for this particular case, we really looked at a multifunction prosthesis that had an elbow, a shoulder joint, wrist rotation, wrist flexion, and the ability to open and close a hand as a case example of what might happen if someone wished to control a multifunction device using only a single voluntary channel and a single button that lets them switch back and forth. Again, this is very close to many clinical deployed solutions for people. And I'll show you a video here. This is just a very simple task. We've asked this individual to just move the robot arm back and forth across a workspace. And on one side, I think it just wave the hand. And on the other side, I think it's open and close the hand. And so right now, you can actually, he's switching between functions with his right hand, as you can see. We did that to make it really nice and visible. And at the beginning, he's forced to sort and select between all of those different functions of the limb. Within 30 seconds of learning, the system's already started to build forecasts or predictions about what he wants and starts to give him what he wants when he wants it without having to do that voluntary switching action so many times to switch between the modes or functions. It's optimizing. Predictions are being used to optimize his control. And he makes that face like, oh, wow, that actually worked. And now he's just tapping his hand once every time he goes to these different parts of his workspace. You can think of it, I had to show one graph with wiggly lines. I am a scientist. Actually, I showed two. Oh, maybe I'm overdoing it. But in this case, this system is continually learning to predict the different modes or functions that a person actually uses, and then what time and when they might actually use those modes and functions. If I'm doing a task, like I'm grabbing this, I'm moving it over here, I will be doing a sequence or a staging of different motions. In this case, the system is starting just to learn to predict that, and it does something really simple. It takes its predictions, the machine, the robotic arm is taking its predictions of which joint's going to be used next. And it just does something ridiculous, it just rank orders them. And then when the person starts to switch between those many modes and functions, they just get the thing that they probably want next. And if they don't get that, they get the next thing. This happens on all of your phones and computers. But this is the first time we showed it could be actually deployed on a prosthetic limb and learned through real-time experience. I won't dwell too much on this, but it really, we found it was able to dramatically reduce the amount of time it took for someone to complete, say, a picking and placing task, reduce the number of manual control interventions. And Ann Edwards had some extension work that showed the system can also learn to switch for the person. It can learn with high probability when to switch through experience, through watching the person making forecasts of the person's actions, and be able to streamline the interface beyond what would even be possible with a classical or fixed switching system. In the interest of time, I'm going to switch the proof in the pudding kind of video where I show like a head-to-head race between the two systems. But I will say that the adaptive system finishes much, much earlier than the non-adaptive system. So that was just one example. I'll say that we have shown that we can also, there's some recent work with Vivian Mouchouar's team and especially her graduate student, Poria Faridi, looking at that we can apply this exact same idea to switching between different walking modes and functions in a lower limb exoskeleton. So someone using exoskeleton technology. It was also applied in different ways to other work from that group on intraspinal microstimulation. We've looked at it at robot failure, like robot limb failure and anomaly detection, hazard prediction and learned feedback in both robotic limbs and also virtual reality decision-making tasks, and coordinating synergies in upper limb robotics. If you want all the joints of your hand to work together to catch a ball, we've shown that those continually learned predictions can also be used to create these joint synergies, much like they are in our biological systems. So it's not limited just to picking and placing with a robotic limb, as I showed you. And I will also say that I really like this study. It was one of the first demonstrations. It was proved that control learning is very hard. We also showed that a system could learn just through feedback from a person to interpret that control pathway, to interpret the signals from the human body and map that to control signals for a robot limb. In fact, this study showed that a person could train a robot limb just like a puppy, just giving positive and negative rewards to actually train a bioelectric control strategy that was completely driven by the person. There was no a priori experimenter fixed, like this is good, this is bad function. The person literally just clicked the button saying, yeah, good, nope, bad, yep, good. Now, clearly that would be intractable if it was deployed exactly like that. But the takeaway message, you can in fact train a neuroprosthesis just like you would a puppy. You just might not want to. Okay. Continual learning, that was the case example I wanted to walk you through. I'm going to sort of take the now winding road to the end by way of a few, I think, really cool videos. But in the meantime, I want to say that I pitched you continual learning, and continual learning is great, but it also enables constructivism. And in terms of constructivism, many of you might be familiar with it in terms of people like Jean Piaget, looking at early childhood learning and development. But it really is the idea that things like perception, knowledge, understanding, and abilities are constructed through interaction experience. And that this is inherently a continual additive adaptive process. So when I start to talk about continual learning, and what might be continually learned in a neuroprosthetic device, I'm really thinking that it does enable constructivism, that continual learning and constructed control and feedback is in essence putting the person first in our assistive technologies and their goals and needs. It's tasking the device itself, in fact, to change to the person and with the person as they live their life so that it can do the things that they need to do in their daily life. There is solid evidence, and this is what I hope you've seen a glimmer of, at least in my talk today, that there's solid evidence that is actually possible. That now we are at that tipping point I pitched you early, that we are at a place where our technologies can adapt to us and our needs as we're using them, that is computationally, technically possible with present prosthetic hardware, not the hardware of the future. And then there's the questions like, is this the right time to then push very hard on this? What evidence do we need? I will suggest that we do need to start working on this right now. And in terms of critical evidence, I've got a gigantic list. We can talk about that some other time. But one of the key pieces I think that we do need to create evidence for, and that's where I see a lot of the focus of my work going in the next 5 years, especially, is the trajectories of long-term co-adaptation between the person and the machine as they are both continually learning. There's like, from any given starting point, like if any two of you were to become dance partners and go into dance competitions, you would have this continual adaptive process of changing to each other and learning about each other to become a really functional dance partnership. In the same way, a person and their assistive technology will, from any given starting point, go through a trajectory of co-adaptation. I think we really need to understand those trajectories of co-adaptation and how those trajectories are altered by the choices that we as designers might make in terms of things like the physical design of the system, the kinds of artificial intelligence methods that we deploy, everything from the kind of prediction learning to really like, wow, did I use like a deep net or this other thing that Patrick was using? So that's the kind of evidence I think we need. I'll show some of the technical systems that we have because we're pursuing this now, and we're sort of throwing at this a number of the technologies we've developed in our lab. A lot of these are open source technologies. So I'm showing you here the bento arm and the handy hand. Those are both fully open source. They're designed with to have parts and also additive manufacturing, so they're accessible and inexpensive across the globe to the best of our ability, so that it can actually include not just like North American development. And they're currently in use all across the world, in North America, in Europe, in the Middle East, in Asia, and Australia. So this is a example of some of the mechatronic technology that we've developed in the lab. They're cool. Okay, well, I'm gonna stop because otherwise it's cool. Here's a example of also we've developed adaptable sockets. So the mounting systems for people to actually engage with technology. This is my PhD student, Adam, who's shredding on a guitar using what we call a bypass prosthesis. The same kind of bypass prosthesis I'm showing you here can also be used with the hand in a different configuration, so that it could be used by someone with limb difference. It could be mounted to someone who has neuromuscular considerations, such that they maybe can't have full control over their hand and arm. And this was created with German Aerospace. We've also started to study frameworks for thinking about how the people and machines interact. There's a very cool framework from human-human interaction called joint action. The idea that two parties will both monitor each other, make predictions about each other, and adapt to each other with knowledge of their shared goals to bring about shared change in their shared environment. And so we've started to study neuroprosthetic control from the lens of joint action, and also start to study how two systems, say a person and their prosthetic limb, might start to build up communication resources, what we've called communicative capital, so that they can streamline, smooth, and optimize their relationship over longer periods of time. Good, still okay on time. I talked a little bit about nerve reinnervation surgery, so I'm going to skip over this a little bit, but again, I'll just remind you that we also now are world leaders, especially here in Edmonton, in surgeries that allow people who say have had an amputation to have their nervous system rewired to give them extra control sites or extra sensory sites on their body. And with respect to that, I'll just show two examples. The first is in fact motor control. So this is someone, again, with nerve reinnervation surgery on the motor control side, moving a series of small objects, controlling all of those different joints. So using some of that adaptive switching technology I told you about, using those to control and move a series of objects across a barrier, also using continual machine learning. I just want to highlight that. And the second here is really cool. This is, again, work that was led by Jacqueline Hebert, and it is object grasping. This is a person with sensory reinnervation who we've asked, they have blindfold on, they have noise canceling headphones. We asked them to use their reinnervated muscles to control this robot arm and squeeze different objects of different stiffnesses. And what they reported here was they could say, I'm touching an object, I'm squeezing as hard as I can, I'm lifting it, I'm dropping it, I feel it drop my grasp. They were feeling what the robot felt in the hand they no longer have, by way of transmitting what the robot feels back to the actual reinnervated sensory nerves on their body. So this is pretty bananas cool. I'll also show one example. This is another cool example of using learning through trial and error. This is reinforcement learning from demonstration. Here we have someone with an amputation who is in fact trying to show a robotic limb how to move and how to interpret his signals by demonstration. So he's using his biological intact limb to show the other limb how it should move. And so this is like any learning process. You can see here it's actually learning. It's not great. It does a little bit of bounce because of the mounting of the robot arm, but the robot arm, the mechanical robot arm is in fact a left hand, and he's showing just through mirroring, sorry, my mic goes out, exactly how the system is supposed to move. So this is a really cool, different way of thinking about training a system in a continual way. And as sort of a second bit, we've spent a lot of time over the last 6 years looking at assessment protocols, gaze and movement analysis, a detailed investigation of not just how a person is moving as they use an artificial limb or assistive technology, but the conjoint of that with how they're looking and attending. I said earlier, wow, if I didn't have any feedback from my artificial limb, I'd watch my hand as I grab this cup. And so we can actually measure that. We can track that. We can see how interventions like sensory reinnervation or advanced machine learning for signaling actually change the way that someone looks, the way that they move, the way they compensate as we add different joints or modes or functions, how it changes their biomechanics and their attention and their decision making. So we're now at that point. And also, I'm just in this video, you can see everyone loves deep nets. Deep nets are great. There's a deep neural network running on that system to move all of the joints. It's super cool, but not the point of this talk. Anyway, deep nets also work. So I'm coming into the home stretch here, and then we'll have time for questions, I promise. In that the take-home message here, we talked a lot about continual learning and how that is able to change what assistive technologies can do in concert with a person. And really, the main message then is that I showed you the control pathway, the feedback pathway, and those interventions, is that constructing and adapting that universal glue between the person and the machine unlocks transformative change in neuroprosthetic interfaces and assistive technologies writ large. It does something, and this is like, I think, sort of the very speculative claim on my part, and you should all feel free to disagree with me and yell at me again over the lunch break, but is that we are now at a point to do something that we could never do before with any of our assistive technologies. For decades, for perhaps more than that, we have looked at channel coding, stuffing bits on wires, trying to take information from the human body, encode it on a channel, and decode it in a machine, and vice versa. Take information from, say, a robotic device, stuff it and compress it onto a wire, and then pop it out the other end and hope that we conveyed some of the information. We've tried to think about human-machine interaction by way of coding channels. But if we have systems that can in fact begin to build diverse predictive models of the world around them, they can actually start to learn through interaction, then we can get to things that look more like joint action, as I pitched earlier. We can get to what Tom Scott Phillips would say was ostensive inferential communication, where one party makes an act of ostension, makes something visible. Like I nod over at our friends over there, and I look at them, and they tell me, you're almost out of time. I didn't have to ask them if I had time. I can make small gestures of ostension, and they can use powers of inference to change their models of me and use those models to, in fact, transmit massive amounts of information in a very short amount of time with very, very little bandwidth. We can start to move to what almost feels like telepathy between humans and machines. And this is now technologically possible because of continual adaptation and sculpting and the computational power of the models that systems can generate. We can actually get towards continual learning in tightly coupled learning systems, much like J.C.R. Licklider would have imagined. Things that do, in fact, think like no human has ever thought before and process information like no information processing system in the history of our species. So with that, I'm going to close and say thank you very much, all of you, for listening to me pitch these wild and wacky ideas, and I'm happy to take questions. Oh, I will also say, if you want to see a robotic limb maybe fail in front of 2 million or more viewers, we'll be presenting the rock music album of the year at the Junos opening night tonight on CBC music.ca. So I'll have to actually be up there with a robotic limb on stage at the Junos. It might be a glorious failure. Stay tuned. If you're interested in watching a limb possibly light on fire on stage, please come watch that, but you don't need to. Cool. Questions? Oh, we're still really on time. Yes, please.
Yeah, talking about wild and wacky ideas, I love that. Great conversation. I was thinking, just from a purely conceptual standpoint, like a lot of the stuff that you've shown is like robots trying to mimic human limbs. And my question was basically, what role do you think that, coming from an evolution standpoint, evolution is a fairly slow process. It's like, if you look at the way that we as humans have come about, it's fairly slow process. But if you would have an engineer and ask them to construct a human body, it would look completely different. So my question is, like, what role do you think can AI play in the development actually of such prosthetic limbs? And maybe they would look completely different based on the information that we require and the tasks that we give them.
I think I'll step back. I love that question. I think it's great. I'll step back and just say that I think for people with limb difference, many would express that, I can't speak for them, but many would express that and have publicly that in fact, a thing that looks like a hand isn't the right thing at all. If you want to go play pool, you're going to have an adapter so that you can hold a pool cue. If you're going to play basketball, you're going to have a specific adaptation for basketball or rock climbing. Hugh Hare from MIT is he's a rock climber and also someone who has lost both of his legs due to frostbite in a climbing accident and has specific adapted lower limbs for climbing so we can go back to climbing. So like already we see that, well, the thing that looks like the hand isn't absolutely the right answer. And the usual ways we control systems maybe aren't the right answer. So then we get to your question, which I think is a really good one, in that, well, if the control can like just looking at the control side, well, if control can completely adapt to what someone actually needs, then we're no longer pinned to escorting some comp into a firmware and that's what they get after they leave the clinic. Well, okay, that can adapt to what they actually want the system to do. Then we see additive manufacturing. We see people who get fitted with a prosthesis and they go home and they 3D print a cell phone holder to put on the arm. That was outside the clinic. They just literally duct tape it on or sticky tape it on there, and it's awesome. It holds the phone, and so they can actually type on their phone and text and things like that with their other hand. And so I think we're starting to see where people can adapt devices themselves. The devices can computationally adapt. And then you can put those two things together and maybe you get great suggestions from the system as to, hey, we often do this kind of thing, but it's kind of inefficient. Could we craft something that looks a little bit more like this to streamline our joint interactions? And I think there's a really cool space there. That space has to be done also with interaction with clinical professionals. There's a cyberpunk Wild West here, which of course, exactly. I think we can all imagine in our mind's eye. But it is actually something that's quite possible now. You can start to think about, again, that trajectory of adaptation and interaction between a person and the devices. I'm going to say devices, like that last slide I showed with all the wires going everywhere. Those devices that support them in daily life. We already do this with a lot of our devices. I think it's only going to change as we start to see the ability to fabricate more physical solutions in a very at-home, efficient, and effective way.
Great, thank you so much.
So it's a really cool question. I'll repeat it for you if you shout it out. Yeah, this is a great question. So I'll just repeat the question. Please tell me what Elon's doing. No, kidding. The question is, in fact, well, all the examples I've shown deliberately, in fact, are very low bandwidth. There's only a small number of channels. Heck, we're using muscles as amplifiers of nerves, and everything I've shown, this is the clinical standard for the most part, is that nerves will go to muscles. Muscles will be sort of a gross signal when there's lots of smaller signals there. If you go back, as was suggested, back to the central nervous system, you might have thousands and thousands of recordable channels that might be also moving. I'll respond to why we choose this area. I'll also comment a little bit, as you asked, about the sort of the higher density interaction channels. One of the reasons that I like to focus on the peripheral nervous system is that there's already been some sorting done on the part of the nervous system. Different channels are also they're well codified into their sensory and feedback dimensions. And in addition to that, they're largely stable over time in a reasonable way. Of course, there's a lot of plasticity in the human body, but as you start to get downstream towards, say, a residual limb, you do actually get a nice sense of stability. So anytime you have two parties that are co-adapting, it's really hard if both parties are adapting really, really, really rapidly. And this is found, so getting to the central nervous system, this is what folks like Jose Carmina and others have seen, is that in fact, if both parties, the person and the machine that's interacting with, say, central nervous system recordings from the cortex, if both parties are changing really, really quickly, there's this inherent instability, or there can be inherent instabilities in that interaction. So I quite like the peripheral nervous system. There's also the clinical impact is that the majority of things that someone might actually use that they might be fitted with in the clinic right now will go off of those sort of mappings from those low bandwidth peripheral nervous system channels. That's what people are getting fitted with. So when we build technologies, we know they can actually get used by people tomorrow, as opposed to farther down the road and like central nervous system interactions are still a bit farther off from becoming a clinical standard. So now, okay, what about high density communication? That sounds really cool, right? I think the answer is yes. So, am I running batteries out? Maybe. The company you mentioned earlier, like there's Neuralink, there's Paradromics that is looking at 10,000 sensors per square centimeter. So there's work by Brown University Intel looking at bridging the spinal cord on spinal cord injuries. And they have high density sensors that are going from one part of a spinal cord to another. These are high density interactions with the central nervous system. They are characterized by, say, faster adaptation. And that is something that's actually really cool, but it also does give some kind of difference in the space we're talking about. When I mentioned things like extensive inferential communication, it means that we do actually now have the potential for a lot of inference and a lot of extension. And that is something I think is really exciting. So I don't want anyone to think that I'm ruling out central nervous system interactions for clinical translation. I think some of the lower bandwidth channels are the right way to get, say, adaptive AI technologies into use by people who use assistive technologies in the very, very short term. But the potential for that beautiful co-adaptation of those two intelligent systems, a person and machine, by way of high bandwidth channels, in the same way that we can imagine what I said was almost like telepathy across a single channel or a low bandwidth channel. Imagine the potential when you then extend to those higher bandwidth channels. I think it is a multiplicative factor that is not to be discounted. It's really quite exciting. Yeah, a lot of the Neuralink technology does jack into the, from my knowledge anyway, is into the cortex. Yeah, much like Paradromics and the others that I mentioned. There is some interesting work in higher density recording downstream, but it is again, the higher density recording downstream. There's questions as to the utility of that many recording channels. Dario Farina and others have shown that there's some neat stuff you can do where you do actually record like quite densely from slightly downstream connections, even farther than the spinal cord. And that's really cool. Like it's still outside the central nervous system or inside the central nervous system. There's some neat things you can do based on the time series of the data to be able to infer all sorts of things about motor control. It's another topic, but it's also really, really, really cool. More questions. I see a question. There's one right here coming, and then we can.
Hi, thank you for the presentation. It was extremely interesting. I had a quick question about the timeline for co-adaptation. And I understand that it would differ from individual to individual, but how do you think the timeline will change if there was some prior knowledge included into the adaptation? So I'm not saying, so for example, you mentioned rock climbing, right? And I know that's a very high intensity adaptation, but if I know one person who is using a prosthetic limb adapted to rock climbing from their point of view, is there any prior knowledge we can use to forward into someone else who is also using a prosthetic limb? And how does that change the time?
That's a great question. I think there's some reasonable evidence. I've seen evidence going back to even 2013. There's an interesting paper on sort of that transfer learning idea, not in terms of specific activities, but saying, hey, it does take a lot of time for a person to adapt to their device, and it often takes a lot of just samples for the device to be able to be used by the person. Like there's now commercial systems where a person can push a button on their limb, and the limb will do a bunch of motions. They try to make what they think is the motion that will generate it, and machine learning makes the mapping for them. They can retrain it. That's been a huge improvement, but for a very long time, it took a lot of samples to get really good training. And even in the work I showed, it takes a lot of data. So that early paper showed that, yeah, you can actually start to record from many different individuals, put it on a new individual, and it will sort of figure out the right combination of those prior models to have a good new starting point model for that person. We have work in our lab by my co-supervised PhD student, Heather Williams, who's looking, in fact, at transfer learning for more advanced neuroprosthetic devices, like for something called the limb position effect, which is like reaching up and trying to put something on a shelf. Often the muscles just mean that the limb misinterprets what the person wants and like drop stuff. And she's looked a lot at that transfer learning idea and for specific reaching motions and like compared against different individuals and showed that you can, yeah, in fact, quite nicely draw some of the information from other individuals to speed the training and adaptation process for a new individual. So yeah, that totally like there's some good evidence that works. In terms of doing that for specific activities, I don't think there's anything right now that has compellingly showed that, but it's a really cool place to start because then it does mean like, oh yeah, you get like user communities. You're like, hey, you want to check out my model? Like I have this cool like rock climbing model. Do you want to like why don't you like hard boot that into your bionic limb? Clearly there's all sorts of issues with what I just said, but yeah, exactly that. Thanks for a great question.
Sorry, just one quick announcement before we get to more questions. I won't cut you off, I promise. We're going to start doing lunch here soon. So if anyone has a dietary preference, could you please just fill out that card that's in front of you and just put it on the place in front of you? And then one more announcement, just people who have a booth, we're going to meet you outside the Amber Room at 12:30 when we open the doors back up. And then we'll go in there with you. So yeah, back to questions.
Cool. Maybe last one. Is that sound good? Two more. Okay, I see two. Oh, two more questions. We'll do two more questions if that's okay. Okay, please. Yes.
Super quick. What was my question? Forgotten now. Oh, so for people saying like with neurological disorders, so they've got, maybe it's they have their limb, but they just can't seem to communicate, to that limb very well. Is there, can this be adapted for that kind of, disability or other ability, I guess?
Yeah, there's a really, I'll sort of jump to some of the work from the Cleveland Functional Electrical Stimulation Clinic. They did some really neat stuff back in the early days of the BrainGate project. This is a project to tap into the central nervous system by way of the cortex. And it was with old Utah arrays. So, I mean, I say old now, then it was really novel, but like, arrays of 100 electrodes implanted within the surface of the brain. And what they showed is that for someone with spinal cord injury, in this case, that they could, well, you could actually not just do the thing where the person controls a robotic limb, but they could just sort of skip step across the break and then reinnervate by way of stimulation, electrical stimulation, the muscles and nerves of the body. So the person could in fact almost remote control their own body. And this was really neat. It's very sort of on point because that was for complete spinal cord injury, but there's other examples where in similar cases where there might be incomplete neurological injury or something to someone who's trying to perform motor control acts, that you can in fact use the same kind of machine learning technologies to bridge that gap and be able to help augment, accentuate, or transform their motor function in whatever ways. We've looked at people with spasticity, in fact, and looked at how we can use machine learning in the same way we do for prostheses to be able to help control exoskeletons or other adaptive devices. So yeah, it's really, it translates really nicely to a wide, that's why I titled it Assistive Technologies. And like, I really think this is broader than just prosthetic limbs, although that's what I work on mostly. So yeah, it's a great question. Lots of translation there. All right, last question, please.
Hi, I really like the talk. Thank you so much for presenting. I thought it was really interesting, the technologies you brought up where it can connect directly to severed nerves. I was wondering if you thought that we might see a day where it becomes more efficient or more cost effective for folks who aren't necessarily missing a limb to operate things using connected nerves rather than their own body. Like for example, you could, like if there's applications to surgery where the human hand is only so steady, but maybe a robot can do it better, or a crane can be more precise, or what do you think? Do you think there might be one day technology where the human body gets replaced in some jobs?
You looked at my lab and saw our third arm. You've been looking at my lab, haven't you? We actually have a third arm that you can wear that comes out of your chest in the lab as one of our ways to study like how you might augment or extend abilities for individuals in ways they need. That one's not controlled by jacking into the nervous system, but I'm using it as we do actually have that. But it's a cheeky example of how, yeah, like I do think a lot of what we're seeing now is a tipping point in other neural interface technologies where like, do you want to just beam yourself into another body? Well, I don't know. You can make your own choice there. But can we use our limited channels of information in our body? Like I talked about getting away from code channels, like not just stuffing bits and wires. I think technology makes it possible now for us to do what Like you asked me 10 years ago, I would have said, okay, to use that third arm that we have, it's a wearable mounted third arm. It can move around, grab stuff. To use that, you have to still sacrifice something. You have to give up some of the function you have. As
Mhm.
someone who like, as a person with a normally intact body, to control that, I'd have to like use a thumb joystick. I have to like wiggle my toes. Some of the prosthetic
Right.
limbs you see that DARPA created, they use a toe joystick to control the hand of it. So you have to sacrifice something or temporarily give up using something to get the function of the other thing. I think with technology now, where we're starting to see is that we can actually imagine a class of technologies. Maybe you don't get something for nothing. Thermodynamics police will come and lock us all up if we get something for nothing, but you can get a lot for a little. And that is going to open up, I think, a wide range of non-clinical augmentative technologies that are going to come on the market quite shortly, I suspect. So yeah, I think that's
Wow.
well, watch for it soon from all over the world. Whether it's good or bad, I'm not going to say. I don't know, but I think it's going to happen.
Wow.
Yep.
Thank you so much.
Cheers. Thank you so much, everyone.